Today we're going to be talking about limiting reactants type stoichiometry problems. Now up until this point we've been doing examples, specifically mass-to-mass stoichiometry or three-step problems, where I give you one amount of maybe one of the reactants and ask you to solve for grams of NH3. And we have, in that process, completely forgotten or didn't care about the other reactant, because in stoichiometry problems you can only compare something you know with something you're trying to find. For example, if I start with 10 grams of this and I ask you how many grams of NH3 are produced, we've simply just forgotten about the 3 moles of H2 in this process. But in a limiting reactants problem, I actually give you 2 starting amounts. And so maybe I give you 10 grams of this and maybe like 6 grams of H2. So what's different about these problems is instead of one starting number, you in fact have 2 starting numbers. Now, a novice or someone who's beginning to develop this skill will probably try and add those 2 masses together. They'll say, oh, just add them together to make 16 grams. Well, in fact, you don't do that. You don't add them and you don't average them. You in fact need to do 2 mass-to-mass stoichiometry problems. The first one is going to go from grams of N2 to grams of NH3. And the second one is going to use the other mass, grams of H2, also solving for grams of NH3. So in other words, you take both starting amounts and you do 2 problems, both solving for the same amount, the same molecule on the other side. So let's go ahead and do that. Let's take and solve 10 grams of N2 for NH3 and 6 grams of H2 for grams of NH3. So I'm going to start with 10.0 grams of N2, and we've done a number of these already, so this can go fairly quickly. You're going to go from grams of N2 to moles of N2. So the molar mass of N2 is 28.02 grams of N2 for every 1 mole. Now the mole to mole step, which is going to grab the coefficient from N2 out in front, and I'm going to also grab the mole for NH3, which is 2, which is out in front. So 1 mole of N2 for every 3 moles of NH3. And finally, I'm going to go from 1 mole of NH3 is equal to 17.04 grams of NH3. Now I'm going to put that into my calculator and find an answer. And if I take 10 grams times 3 times 17.04 and I divide by 28.02, I'm going to get an answer of 18.2 grams of NH3. But I'm only halfway done with this problem. I in fact need to do another problem, this time starting with 6 grams of the H2 and also solving for grams of NH3. And once we get those answers, I'll tell you what to do with them next. So let me scroll up to give myself a little bit more room. Now I'm going to start with the 6.00 grams of H2 over 1, and I'm going to multiply by having grams of H2 on the bottom and moles of H2 on top. 1 mole of H2 is equal to 2.02 grams. Again, that's the molar mass, which I can get by adding 1.01 plus 1.01. So grams will cancel. Next step is to do the moles of H2 to moles of NH3 conversion. And so as it was before, there's 2 moles of NH3. And then it just occurred to me that I made a huge mistake on this first one, because this should not be 3 moles, this should be 2 moles. And if I go ahead and calculate this number again up in the first example, the answer is actually 12.2 grams. So my mistake there. Anyway, back to the second problem. I still have 2 moles of NH3, but on the bottom I have 3 moles of H2. The 3 moles comes from the balanced chemical reaction up here, up above. So I finish this off the same way I finished off the other problem, by going from moles of NH3 to grams of NH3 using 17.04 grams per mole. And I punch that into my calculator and I find that the answer is 33.7 grams of NH3. Now at this point I have 2 answers, and one of them is the correct answer and one of them is a false answer. The one that is smaller is the correct answer. And so I put a box around the one that is the smaller of the two numbers. And this is why. Think about this. If you have two masses, both starting amounts of reactant, they're going to use up each other as the reaction proceeds. It's going to create NH3. But the one that gets used up first limits the reaction. And if it limits the reaction, it produces the lesser amount of the product. So the one, it's not the one that you start with less of, it's the one that produces the least amount of product, because it's the one that runs out first. In a limiting reactant problem, the limiting reactant is the one that runs out first. And in this case, the limiting reactant is the one that produces the lesser of the two answers. So the answer is 10.2 grams, 10 grams of N2 is my limiting reactant, or just say N2 is limiting. Now the other reactant is known as the excess reactant. And the reason that it's called the excess reactant is because excess means extra, so it's the one that doesn't run out. In this case, it's the H2 that is the excess reactant. So if I ask you to identify the limiting reactant and the excess reactant, you got to go back to the beginning of the problem and decide which of the reactants runs out first. The one that produces the less amount is the limiting, and the one that produces the greater amount is the excess, and the lesser amount is the answer. So I'll let you know that there's oftentimes students lose points, and the way they lose points on these problems is they do everything correctly, but they circle both answers. And then I say, which one is the correct answer? And then they tell me, well, you know it's the smaller one. And I go, I know it's the smaller one, but do I know that you know it's the smaller one? So you have to identify one answer as the correct answer. Circle it, point to it, star it, whatever. Just say, this is the answer. I will ask you an additional question. I'll say, what is the limiting reactant? And the students will say, oh, I'll just label it like this. I'll just go limiting reactant. And I go, no, that's the answer. The reactant, it has to be something that you began a problem with. It has to be a reactant or something from the left side of the chemical reaction. So you don't want to label it there. You don't label limiting reactant at the end. You say the limiting reactant is the one that you begin the problem with, and that would make this one the excess reactant. Another thing you want to look out for and try and avoid is when students start to report their answers, what they do is they add these two numbers together or they average them, and you do not want to do that. You simply pick the smaller of the two numbers. So I'm going to write this out on the bottom very explicitly so it's very clear. Don't average them, don't add them, don't subtract them, don't multiply them, don't divide them. Simply pick the smaller of the two answers. I'm going to finish up this video lesson with doing one more practice problem. And here's the chemical reaction. Now I've already used the N2 and H2 so often that I need to come up with a new one. Here we've got some iron being combined with some oxygen gas to produce iron 2 oxide. Excuse me, this is iron 3 oxide. So Fe2O3. The balanced reaction 4, 3, and 2. If you start with 25 grams of iron and 20 grams of O2, how many grams of Fe2O3 will be produced? So as I set up this problem, I've got 25 grams of this and 20 grams of this, and I'm looking for the final product. So I start the first of the two problems using the 25.0 grams of iron over 1, multiplied by 1 mole of iron, and I look up the molar mass of iron, and it is 55.85 grams per mole. Next up, I write out moles of Fe down on the bottom right and compare that to the moles of Fe2O3 in the top right, because I'm going to do the mole to mole step. And I'm going to put 2 for the top and 4 for the bottom. So 2 on the top, 4 on the bottom. And I finish with moles of Fe2O3 on the bottom and grams of Fe2O3 on the top. Now I'm going to need to use my periodic table to add this number up. I need 2 irons plus 3 oxygens. And that number is 159.69 grams. Now that I have all my numbers set up, I can punch these into the calculator. And the answer to my first half of the question is 35.7 grams of Fe2 H2O3. Now I'm going to do the same setup, but this time I'm going to start with the 20 grams of O2 over 1 and solve for grams of Fe2O3. So I start with grams of O2 on the bottom, moles of O2 on the top. 1 mole is 15.999 times 2, which gives me 31.998, or 31.99, excuse me, just 32. So that just rounds up to 2 decimals to 32 grams. Then I go from moles of O2 to moles of what I'm trying to find, Fe2O3. And again, there's a 2 in the top for Fe2O3, but this time there's a 3 on the bottom for the O2 because of the stoichiometric coefficient here. And I finish up with the same molar mass step. 1 mole of Fe2O3 is 159.69 grams of Fe2O3. And then I punch that into my calculator and I get 66.5 grams of Fe2O3. So I've got 2 answers, and as I told you on the last slide, one is the correct answer and one is a fake answer. The real answer is the one that gives you the smallest amount of product. And so it's this one. It's the top one of the 2 problems. Even though you started with less of the O2, the Fe gets used up quicker because it has a higher mole ratio, and compared to Fe2O3, it also has a higher molar mass compared to oxygen. So the 55 grams gets used up faster, plus you've got more moles getting used up, that results in a smaller number. Now, you're going to have to do all that math. You're going to have to do twice the math for the same amount of points. Pick the smaller of the 2 answers. If the question also said, identify the limiting reactant, you would go back to the beginning 2 numbers, and the one that gave you the smaller of the 2 numbers is labeled the limiting reactant. So in green here, I'll label limiting reactant. It's the iron. If you put limiting reactant here, I'm going to go -1 because it's not the product. It's not the lesser of the 2 numbers. That's the answer. The limiting reactant is the one that you begin the problem with.
Here's another example of a practice problem that requires some limiting reactants. First, we need to balance this chemical reaction. If you look at the top, I've got 4 phosphorus on the left, but only 1 on the right, so I'm going to multiply that by 4. Now that my 4 has distributed, I have 12 hydrogens, so I'm going to come over here, and 2 goes into 12 6 times. Now finally, I take 6 times 1, which is 6, plus these 10 is 16, and 4 times 4 is 16. So my correct balance is 1, 6, 4. Now I can go ahead and take a look. I've got 135 grams of the tetraphosphorus decoxide, that's its first reactant, and I've got 70 grams of water. So I'm going to set up 2 stoichiometry problems, starting with each one of those. Now the first thing I need to do in this top one is figure out how many grams of P4O10 are in 1 mole of P4O10. And when I look up the molar mass, it's 283.89 grams of P4O10 per mole. Next, I need to do a mole-to-mole ratio. And I'm converting from P4O10, and there's 1 of those, and I'm converting to the H3PO4. That's the phosphoric acid. So there's a 4 in the top of this mole-to-mole conversion. Finally, I need to go from moles of H3PO4 to grams of H3PO4, and the molar mass of this substance is 97.99 grams. The last thing I need to do now is do the math. And if I multiply 135 divided by 283.89 times 4 times 97.99, I get a final answer of, to 3 significant figures, 186 grams. Now I'm going to do the same thing here for the bottom. I'm going to take the grams of H2O, and I'm also going to solve for mass of H3PO4. So first I'm going to divide by the molar mass of water, which is 18.02 grams on the bottom and 1 mole on top. Next I'm going to do the mole-to-mole ratio. This time I have 6 moles of H2O on the bottom, and I'm once again converting to moles of H3PO4 on top, so that's a 4. Finally, I'm going to use the same molar mass as I did up above, so I'm just going to transfer that down here. Once I get all those numbers in place, I punch it into my calculator, and I come up with a final answer rounded to 3 significant figures of 254 grams of H3PO4. Now, comparing the 2 numbers, the one on the top is smaller, so that is the correct answer. This one just gets thrown out. Students might just try to save themselves some time and work by simply going to the original numbers and go, oh, I have less water. So obviously this is the one that's going to run out first. So I'm not even going to bother doing this second set of work. Well, as you notice, starting with less doesn't necessarily mean it produces less. In fact, starting with less produces more. So don't just look at the starting numbers. You have to compare the two values at the end and decide which one is the correct answer based on which one is the smaller of the two. Now let's take a look at this follow-up question. How many grams of excess reactant will be left over? Well, we know that the P4O10 is the limiting reactant and the excess reactant is the H2O. And we're trying to figure out how much would be left over. Well, I had 70, but I'm not going to use all 70. So this is actually pretty simple. We're just going to use our process of stoichiometry once again. But this time, instead of taking the limiting reactant and solving for H3PO4, I'm going to take the limiting reactant, because I know that's the one that's going to run out first, and I'm going to solve for grams of H2O. Once I solve for grams of H2O here on the end, I'll get a number, and I'll just subtract that from 70 to figure out how much of the excess was left over. So all the numbers are pretty much here in the work up above, and so you can just go ahead and translate those numbers down, piece it together, and solve the question here at the end. So my molar mass, once again, is going to be 283.89. So I'm going to put 283.89 grams on the bottom and 1 mole on top. This mole to mole ratio, though, is going to look a little bit different. I'm going to put 1 mole of P4O10 on the bottom, and I'm solving for 6 moles of H2O on top. Now I'm going to use the molar mass for water once again. I'm going to put 1 mole of H2O on the bottom and 18.02 grams on top. Once I got all these numbers written down, I'll punch into my calculator, and I'll get a final answer to 3 significant figures of 51.4 grams of H2O. Now, obviously that's less than what we started with, which is good because we didn't use all of the H2O. So you just take 70 and subtract 51.4, and you get an answer of 18.6 grams of H2O left over. Well, that takes care of this video lesson on limiting reactants. Thanks for watching.